What's happening? Where are you? Here you are. Okay. Start. This looks good. Okay, recording is on. I guess we are good to go. There are the links to our website again. I already pasted them in the chat, so you have them. And I will just jump right in and tell you a little bit about our philosophy and priorities. So our graduate program is designed to provide you with a wide range of technical and critical thinking and problem-solving skills that you really need to be successful in your professional and also in your personal life. So we are not only providing what you need to navigate the program and end up with a degree, we are really trying to give you everything that you need for a successful career. So we do this with several different approaches. One of them is a very flexible coursework. We have very few required core coursework that depends on the division you will be joining. Most of your coursework will be completely open, and you will discuss this with your research advisor and adjust it to your research interest and to your project, right? I already mentioned you will have access to state-of-the-art research facilities. And of course, this is always important because your research really depends on the instruments or on the facilities that you can use for the research, right? They are producing the data that you need, and this is very important. You will also have an advisor, a research advisor, who is doing cutting-edge research. And this means that your research project will have real impact on the field. So you're really close to what is going on in your research field, and you will have the potential to work on a project that focuses on really important research to solve, for example, global challenges like energy and health. We are also putting an emphasis on individual mentoring, so you will have help and guidance while progressing in the program. We have clearly structured degree requirements, and so you will not get lost in our program when you join here. So in summary, you will have the opportunity to gain real-world training, and your training here will enable you to really make an impact in your area of interest. And so this is what you will get from us. On the next slide, I must say, I really regret that you can't be here on campus. Our campus is really beautiful. The Princeton Review has described the University of Delaware campus as absolutely the most gorgeous anywhere, and I completely agree. It's actually already beginning to be spring. I took this picture of the cherry blossom here just this morning. They are starting to blossom, and they are everywhere on campus. Again, on our recruiting website, there are several aerial footages of the campus, so you can get an idea how beautiful it really is. Our university was funded in 1743. Trying to get a spotlight here. We have around 1,200 faculty at the university, 24,000 total students, of which we have 4,500 graduate students. So it's so UD is really a major R1 university, but we have a moderate size. We are not a gigantic campus like, for example, Michigan. We are small enough to be personalized. You probably know that UD has very famous alumni. One of them, of course, our president, Joe Biden, is UD alumni, and he is on campus from time to time. I actually have seen him campaigning a couple of years back in Delaware. So you might see him. We also have the Biden Institute now here on campus. So, but if you are not so much into politics, but more into sports, Joe Flacco is also a UD alumni. He's playing for the Eagles this season, and both together make actually UD one of very few universities that has a president and a Super Bowl MVP. So actually, it's only 4 universities in the US that ever produced a president and a MVP. So long story short, UD might not be among the most famous universities in this country, but it's definitely a place where many good and important things have happened and are still happening. And many people who have decided to come to UD during their career were very successful and have gone to do really fantastic things. So let me say a few things about Newark and the state of Delaware. Some of you might know we are located just in the center here of the Mid-Atlantic region, in the center between New York City and Washington, D.C. Both are about a 2 hours ride. The next international airport is in Philadelphia. It's only a 40 minutes ride, which is really good, really convenient if you're traveling. And the next bigger city you might not have heard of is Wilmington here in Delaware, but I will show a couple of pictures of Wilmington later on. So the city of Newark, you see here on the lower part, the main street of Newark, has really a small college town feeling, which I really appreciate. It's really a very nice college town with I repeat myself, beautiful campus, but it's not in the middle of nowhere like some other college towns, right, or university cities. Actually, it's really pretty centrally located. You can get to big cities like New York City very easily. The state of Delaware is really beautiful. Let me go back to this slide here. We are basically wedged in between the Delaware River up here and the Chesapeake Bay, which is a beautiful estuary. Depending on whom you trust, it's the second biggest estuary in the world. And you can do all kinds of water sports, bird watching, fishing, whatever you want there. I'm sailing on the Chesapeake. It's really beautiful. It's not exactly in Delaware, but it's close by, so you can definitely get there. On the other side, on the Delaware side, we have beautiful beaches. Apparently, some people claim that these are the most beautiful beaches on the East Coast. I'm not sure if Outer Banks will agree to this, but they are not here. We have large state parks that are really very nice for spending time outdoors. So I'm hiking a lot actually in the mostly in Pennsylvania and in Delaware here in the state parks. And I mentioned Wilmington. Actually, if you are more into kind of city life, Wilmington is not a big city. It's around 100,000 people, but it actually has a kind of big city feeling to it. It has a very nice riverfront with bars and restaurants and shops that you can stroll and enjoy on weekend afternoons. So it's certainly worth a visit. So take home message, there's definitely something for everyone in Delaware. It's really a very nice place to be. Let me come back to our department. So a few departmental statistics. So our graduate program has really a long history. We awarded the first PhD in chemistry in 1948. We have around 30 research active faculty, 200 doctoral students right now. You all know that our stipend, our yearly stipend, is around $30,000 a year. And usually this is actually increasing every year. We have research programs across all of chemistry and biochemistry, as well as many related fields. And our external funding is pretty big. It's actually 10 million per year. And if you compare this to the moderate size of our department, the 30 faculty, this is really a pretty well-funded program. To buildings, so our department is distributed across 3 buildings. It's Brown Lab, Drake Hall, and Lamotte Dupont Lab here. We have around 215,000 square feet of research and teaching space. The good thing is that these 3 buildings are connected. So you don't have to commute between these buildings if you want to go from one to the other. In fact, sometimes you actually leave one building and enter another building without even knowing it. So these buildings are pretty recently renovated. They have really kind of modern research space, but we are also expanding regularly. Right now, we are building an extension to Drake Hall. This will be the new Drake Hall. Most of it is already standing, so it's still wrapped up. The walls are missing, but the building is basically already erected. So very soon we will have new research space in there and new teaching space. We have also an extension to our campus recently, maybe 6 years ago or so. We got this Star Campus, which is about a 15-minute walk or a couple of minutes ride on a bus, where we have a lot of biopharmaceutical companies and programs in buildings that are really built every year, another building, and there's still a lot of place. And I know that many people in our department are involved in some way in research that happens at Star Campus. Our faculty are really all recognized leaders in their disciplines. So this is a snapshot that is slightly outdated, but all people that are on this, or most of the people that are on this picture, are still here. Our faculty got some really notable awards. You might know that we got the Nobel Prize, or not we, but Richard Heck got the Nobel Prize in 2010 for the Heck reaction. We have actually multiple AAS fellows here in the department, multiple Alfred P. Sloan Research Fellows, Camille Dreyfus Teacher Scholar Awards, multiple Cottrell Scholars, DuPont Young Professor Awards, and many of our young faculty got an NSF Career Award early in their career. We have NSF Presidential Young Investigators among the faculty, and Pew Scholars in the biomedical sciences. So you see that you can really choose between many excellent and highly decorated faculty for your research project when you choose to join our department. Our department is organized in the kind of more traditional divisional structure of chemical departments. So we have an analytical division, inorganic division, physical division, biochemistry division, and organic division. But these divisions are really mostly for organizing the department, for management, and for teaching. You see many names actually are in different divisions here, and this shows you that our research program is really highly interdisciplinary and collaborative. And so I actually like this graph here more, where we associated the different research active faculty. So I am here actually depending on their research, if it's more fundamental or more applied, and also depending on basically their research aims towards energy, environment, and health. And you see we are all over the place, right? Plus, you will also see that we have the planned future hires on this graph. So these are actually faculty that will be added to the program in the near future. So we are growing. And on the coming or following slides, members of the admission committee will present their research area. And this will be another opportunity where you see how collaborative our research actually is. So Don Watson will start, and he will tell us about transition metal catalysis, organic synthesis, chemical biology, and the related facilities. And I'll turn it over to Don.
Thanks, Lars. Yeah, so I just wanted to give you guys a little bit of a taster, I guess, of some of the areas of research around organic and inorganic chemistry that we have here. Eric will tell you a little bit more about some of this as well. One of the big areas that our department has a lot of deep expertise in is in transition metal catalysis. So this is both on in the organic labs as well as the inorganic labs. For example, Joe Fox has developed some really nice catalysis up in the top frame there for building bioorthogonal ligation chemistry, and to going to things like the environmental work that Joe Rosenthal is doing in the area below that. For converting carbon dioxide to reduced carbon products. So I think it's an area that we have a lot of depth and I would say a lot of variety in as well. If Lars, if you can move to the next slide. In the organic synthetic side, again, I think we also have a lot of depth and expertise. Again, this extends from the sort of traditional organic chemistry groups such as BJ Chain's group, which is focused on total synthesis, to groups like mine and Mary Watson's that are developing methodology, new reaction methodology, as well as doing some total synthesis, to people like Catherine Grimes, who are using really complex organic synthesis of glycopeptides to be able to probe biological questions. And then on the more inorganic side, people like Eric, who's in the room, Joe Rosenthal, do a ton of organic synthesis as well in preparing ligands for the metal complexes that they're interested in using as well. So again, a lot of depth and a lot of expertise in organic synthesis. And if it's something that you're interested in, I think we have a lot to offer in that area. And the third area I'll tell you about, if Lars will advance the slide for me, is chemical biology. And this really is, again, very pervasive in the department. It extends a lot across a lot of disciplines. So again, starting with people like BJ Chain or Catherine, who are using synthesis basically to probe biological questions. Catherine in particular, for example, is interested in understanding how fragments from bacteria basically trigger an immune response for things like Crohn's disease. This extends into areas of biochemistry as well. So for example, Jihao Zhuang's group is interested in ubiquitination and understanding how ubiquitination is trafficked in the cell and how that leads to programmed degradation of particular biochemical enzymes in the cell, to people like in the physical division, such as Jody Hayden-Perea, who's in the room as well, who is interested in modeling and doing really high level, beautiful calculations on the structures of large assemblies like viral particles and glycocenters as well. So again, the list of faculty shown there, I won't read you the list, but I think these three areas of science are places where we have an extraordinary amount of depth in the department and a lot of very well recognized investigators. So if these are places you're interested in, we have a lot of offerings for you. So in terms of instrumentation that supports these areas, a lot of the people involved in these areas use a lot of NMR techniques. We have an incredible NMR facility. We have 7 spectrometers that are for use in the department. This ranges from 400 megahertz instruments that are set up as walk-on instruments and have auto samplers that are basically running Qs 24/7, to the 850 megahertz instrument that's shown there in the photo, which is 12, 14 feet high, and is used for really sophisticated biochemical experiments. our NMR lab is so good because it's supported by two really incredible PhD level staff scientists. So Steve Bai is our director, and he's assisted by Caitlin Quinn. Both of them are just amazing scientists that really enable us to do science that we wouldn't otherwise be able to do. So it's not just about having the instruments, it's about having the people to support them as well. If you move to the next slide, Lars. So there's a couple other things that I think are sort of unique about UD. One, we have a relationship with Lotus Separations. So they actually have a site here. The grayscale picture is actually a lab in our building. And the big tank behind it is a giant compressed carbon dioxide tank. So they actually do preparative scale liquid CO2, supercritical CO2 chromatography. They're actually a business, but we have a relationship with them where we can give them materials and they can actually help us do challenging separations. And so, for example, one of the things that they specialize is in chiral separation. So we can hand them, racemates, and they can basically give us back single enantiomer compounds, which is really a fantastic resource. And there's only basically one other university in the world that has this kind of relationship that I'm aware of, and that's Princeton. So we hold ourselves in pretty good company there. And then finally, one of the things that I'm personally very excited about on the next slide, we have a high throughput experimentation facility that is directed by Dr. Jessica Sampson. So the picture of the lab is in the bottom there. Basically, this is a facility that allows chemical experiments to be conducted in multi-well format, so up to almost 100 reactions at a time. And so this has really changed sort of the way that we can approach particular synthetic problems in the department. To enhance this, we have something like 450 different ligands available in the lab. So it really and also the analytical instrumentation to be able to analyze plates in multi-well format. And so this is, again, a fairly unique facility to UD. There are not a ton of these around the country, and it's something that I think really provides some unique capabilities and enables some really unique research in the department. And having a PhD level staff scientist running the lab for us, I think is really, really important. And so you'll get to be able to meet Dr. Sampson, Dr. Bai, and Dr. Caitlin Quinn when in the next session when the facility directors tell you more. And I think that was my slides. Eric, I think the next is yours to talk a little bit more about the inorganic side of the department.
Thank you, Don. Yeah, right. Eric is next, and he will highlight some examples from organometallic and inorganic synthesis and present the X-ray facilities.
Thanks, Lars. Don, welcome everybody. Yeah, so along the lines of chemistry that Don spoke about, we have a lot of core faculty focused on both organometallic and inorganic synthesis. Sort of a differentiating factor here compared to the chemistry Don talked about is, largely as inorganic or organometallic chemists, we tend to focus a little bit more on the chemistry from the metals perspective. But here, really with a focus on small molecule activation. So the bottom left is showing some of Joel's work in CO2 activation, which, given our current situation environmentally, is a very important problem. The middle and the bottom is Klaus's work on O2 activation. So we're thinking about making and designing ligands and transition metal complexes for activating these molecules and turning them into useful products or useful catalysts. We're also focused on inorganic synthesis a little bit more towards the material side. So the sphere shown there, molecular precursors, nucleation, and growth. And some of Emil's work thinking about molecular level design, organometallic, inorganic synthesis to tune the growth, nucleation, and ultimately catalytic activity of highly tailored nanoparticles. And toward small molecule activation, my group's focused on storage of small molecules, catalysis as well. But a lot of our inorganic and organometallic chemistry, if Lars, if you go to the next slide, is focused on building materials that span almost the purely biological side in Laura Kaiser's work on wearable electronics to the really purely inorganic side in the bottom left here, and some of Svil and Bobev's work in making cathode type materials in batteries. And I think a really important feature here is that we're not only focused on the design and synthesis of organic, inorganic, and organometallic materials and complexes. There's a lot of our faculty focused on really precise measurement and understanding the properties of these materials. So this porous structure in the bottom and the center, this is a thing we're looking at small molecule storage. The top right is some fundamental work done in Andrew Teplikov's work. So here we're thinking about material surfaces, but really at a fundamental level, 1 or 2 layers of atoms on a surface and how other molecules can absorb to the surface, and really looking at early stages of a catalytic reaction. And we're really pushing into the biomaterials side as well. On the bottom right, just showing, for example, Joe Fox developed this chemistry. It can essentially very rapidly attach just about any molecule onto certain other types of molecules and use these for molecular imaging, making biomaterials toward next generations sensors and diagnostics and things like this. On the last slide on sort of the hard and soft material side is we really do have a pretty big focus along all of these lines on energy. So the bottom left is again Svilin's work looking at battery materials. Joel is thinking about electrochemical energy storage and conversion. Emil's work on, again, nanoparticles for catalysis, small molecule activation. But importantly, you know, some of the other people on this slide really play an important role in not only helping design, synthesize materials, but in the characterization of these, and ultimately maybe even a little more on the applied side, and how we use these in devices, or how devices can handle, say, cycling in a battery or multiple catalytic cycles. And part of the characterization that we use across organic, inorganic, physical chemistry is X-ray diffraction. So within the department, there's a center that's housed where Dr. Glenn Yap, who'll be at the info session later, is a staff scientist here. I think at last check, he's about the 3rd most cited crystallographer in the world. And we're talking out of thousands of crystallographers. He's in the top 3. So really an expert in his field. And he maintained 2 instruments up in the center, both dual source instruments, so molybdenum and copper anodes. The former a little more towards harder materials. The latter really suited well for biomaterials, biological and biochemical type, proteins and things like this, through just simple organic ligands that my group would make. And here, like all the equipment in our department, it's staffed by trained PhD level scientists, but all of the students who enter our program get to do the experiments themselves, and the scientist is there to help them do these experiments. So you take Glenn's crystallography course, you will be running your crystal structures and solving them, which is a really important part of the whole educational process. You're not just handing off materials and getting the data back, you get to analyze and interpret it yourself. And this is a key throughout all of our facilities in the department. And with that, I'll turn it over to Jeff, who's going to talk a little bit more about the chemical biology side of it and focus in on how we can understand diseases, among many other cool things.
Okay, thanks, Eric. So do you want to go to the next slide, Lars? All right, great. So yeah, so continuing on our different tour of different research going on in the department, we really have a lot of faculty here in the chemistry and biochemistry department working on important biological problems that are really related to human health, using a wide range of techniques from things like biochemistry, biophysics, structural biology, and also chemical biology and computational approaches. And so just a few highlighted examples on this slide are, so for example, you can see number 1 in the upper right-hand corner there, that's work from Jihao Zhuang's lab to develop some different drug intervention strategies that really target protein ubiquitination and deubiquitination pathways that can be potentially used to treat neurological disorders and cancer. Number 2 on the slide shows a little bit of work from Catherine Grimes' lab, from their lab's work to understand and probe this recognition of peptidoglycans in the bacterial cell wall. by different human proteins. And these play important roles in Crohn's disease and some other human conditions like that. Number 3 is from my lab, some of our efforts to understand really the structural and molecular mechanisms that control these different reader, writer, and eraser enzymes that regulate RNA modifications. And so these are actually really important for the control of RNA function and gene expression and are linked to lots of different human diseases like cancer or glioblastoma. And then number 4 in the bottom left is some work from Sharon Rosowski's lab looking at really the biochemistry and biophysics of selenoproteins. These are enzymes, really important enzymes that protect our body from reactive chemicals that can lead to cancer and aging-related processes. And so across all of these different research groups, we really use a wide range of different techniques like enzymology, cell-based assays. We use macromolecular NMR. You saw how fantastic our NMR facility was earlier. Protein crystallography. Eric talked a little bit about that, but we do have really great resources for protein crystallography in the X-ray core, not only including our own in-house diffractometer for those experiments, but robotics for setting up crystallography experiments and imaging protein crystals. And so other techniques include molecular dynamics simulations, proteomics, and many more to answer lots of interesting and important really mechanistic questions in biology and biochemistry. Okay, and then so if we go to the next slide, we'll highlight another one of our facilities, which is the mass spectrometry core facility. And so our department really, I think, has a really top-tier mass spectrometry facility for both small molecule and biomolecule mass analysis and experiments. So this facility has about 10 mass spec instruments, and these include walk-on instruments that are very accessible to students that they can get trained on, come in and use these and operate them entirely on their own. And also cutting-edge, very high-resolution instruments like this brand new Orbitrap Eclipse that was installed actually only a few months ago in the mass spec core. And these higher end instruments really allow you to do some very sophisticated and high sensitivity experiments. Overall, the instruments include lots of different types of mass spectrometry. I won't list them all, but I'll say, we have GCMS, we have LCMS, we have instruments capable of doing MS experiments and preparative LCMS capabilities to purify compounds. As with all of our facilities, a really key point is not just the instruments, but the people who are running them. And so we have 2 really fantastic PhD level staff scientists who maintain this facility, who train students, and help really design and carry out different experiments. And so those are Papani, who's shown on this slide, who manages most of the small molecule analysis and instrumentation. And then Yanbao Yu is our new director of proteomics, who is managing all of our proteomics and biomolecular mass spec capabilities and instrumentation. So overall, this is a really outstanding facility that the department has actually invested heavily in, so that we really have world-class mass spec capabilities that drive really diverse research projects and science across the department. And so I'll stop there and pass it off to the next slides.
Thank you, Jeff. So Jody Hadjian-Perea will present some of our research in computational and theoretical chemistry and our computational facilities.
Thank you, Lars. So we have a lot of really great data-enabled computational and theoretical chemistry going on here in our department. In the analytical chemistry division, we have Professor Sharon Neal and Carl Busch. Professor Neal's group aims to overcome the challenges in analyzing complex or multi-component samples that you might encounter in biological, clinical, or environmental samples through the development of multivariate data analysis methods. Professor Carl Busch's group, they're focused on enhancing the sensitivity or the selectivity of analytical instrumentation by incorporating the mathematical, statistical, and chemometric analysis of the collected data into the design of the instruments themselves. Further, on the physical chemistry side, we have sort of a very strong subdivision of computational chemistry where we have 4 professors, myself, Professor Juan Parrilla, Professor Sandeep Patel, and Professor Edward Lyman. Ed Lyman is an expert in the simulation of lipidic systems and studies the dynamics of membrane-bound proteins such as G protein coupled receptors. Professor Sandeep Patel applies computational methods to study various biochemical systems, as well as develops classical atomistic force fields that account for important chemical phenomena, such as polarizability, to improve the accuracy of our simulation methods. Professor Juan Perilla's group does large-scale simulations of viral systems, including viral capsids and their intact lipid envelopes, as well as develops high-performance computational methods that are required to analyze the very large data sets that these calculations produce. My group is focused on atomistic molecular dynamics simulations of virus systems to elucidate the mechanisms underlying how these systems carry out their functions in biology, as well as how we might take advantage of the unique properties of those systems, such as self-assembly for biotechnology applications. And if we go to the next slide, we have some really nice computing facilities available to us either here in the department or on the UD campus. So in general, each group has their own computing resources, and these may include workstations and visualization equipment that's housed in the individual computational laboratories, or it may include rack-mounted nodes that are housed in the department's dedicated server room, which is just right down the hall here. The server room is also home to several clusters or specialized compute-intensive hardware and storage machines, some of which are shared across multiple groups in the department because we're all very collaborative here. Altogether in the departmental computing facility in our own server room, we have 265 compute nodes, which includes over 10,000 compute cores. We have 110,000 CUDA cores for GPU-enabled computing. We have 4,800 Turing tensor cores for AI and machine learning applications. We have over 1 petabyte of raw disk storage. We have 2 full-time on-site IT support staff, Pat and Justin, who all help us stay up and running with our computational needs. We have a dedicated transfer node with the internet to uplink, which really helps us move data around. We have a computational classroom with 17 workstations for hands-on computational training and workshops. Beyond what we have here in our own server room, the campus facilities are actually very, very nice. We have the Cavernous Community Cluster, which is 126 nodes currently, and we're in the process of ordering a Generation 3 partition that'll be hopefully deployed later this year. University of Delaware also recently secured a National Science Foundation Major Research Instrumentation Award of $1.4 million that enabled the deployment of what's called the Darwin machine, which stands for Delaware Advanced Research Workforce and Innovation Network. And this is a small supercomputer that's right here on the UD campus, which is part of the National Science Foundation's XSEED network of machines. University of Delaware is now a level 2 XSEED service provider, of which there are only a few in the country, so we're really proud of that. Finally, several of our faculty who really do computing intensive research have access to national supercomputers, and these are some examples of resources that our faculty have had access to within the past 3 years. This includes various XSEED resources, leadership class supercomputers such as Frontera and Summit. Summit is currently the top 2 supercomputer in the world, and special purpose hardware such as the Anton supercomputer for molecular dynamic simulation. So for all your computing needs, you can get your hands on it here through the University of Delaware.
Thank you, Jody. Impressive. So now it's on me to give you an overview of our energy and environmental research endeavor. I should advance the slides. So sustainability of energy resources in our environment are, of course, fundamental global challenges, and faculty across the department is working on different aspects such as atmospheric pollutants and pollutants in water, solar energy, and many more. For example, we are trying to understand basic phenomena that are related to chemical conversion in the atmosphere and in water. So questions are, for example, how to detect and remediate these pollutants. And in the top left here is an example from the Rosenthal group. They're developing small molecules that can bind and sense nitrites and nitrates. These are problematic for surface and groundwater and come mostly from fertilizers. They are developing, so the Rosenthal group are developing new platforms to detect these species in the groundwater and then sustainably remove them and eventually convert the pollutants into chemicals that we can use. We can also translate this approach to carbon dioxide, for example, if we're thinking about global warming, climate change. And as we know, present and future environmental challenges are closely related to energy consumption and production. So energy science is a strongly interdisciplinary research area that basically reaches from theoretical physics to social science. But here in the chemistry department, we are working on a bunch of topics, and that is including developing porous materials for gas storage that can help solving the energy storage and distribution problem. So down here is an example from Eric Bloch's group. We are synthesizing organic and inorganic materials for energy conversion and solar fuels production. This is actually happening in many of these groups here. We are investigating surfaces and interfaces to understand heterogeneous catalysis and solar fuel production. Here's an example. We are investigating surfaces and interfaces to understand heterogeneous catalysis. That is also key to solar fuel generation. And we are studying charge and energy transfer processes to guide the design of new hybrid materials for solar cell production or solar energy production. So there are many collaborations between groups that are involved in energy science in the department, but also across campus, and this also includes the Delaware Energy Institute here at UB that we have. In addition to new material discovery, it is fundamentally important to understand the detailed mechanisms of energy conversion. And the DOE report on ground challenges for basic energy science lists several of these requirements for developing new complex material systems for solar energy conversion. And I just want to quote two of them here. One is understanding the remarkable properties of matter that emerge from complex correlations of atomic or electronic constituents. And another one is understanding how to control materials processes at the level of electrons. And research groups in the chemistry department are approaching these challenges with a variety of tools from different angles. For example, by using electrochemistry and photoelectrochemistry to study redox potentials and energy level alignment in complex materials and to measure macroscopic yields and reaction kinetics. We are also using spectroscopic techniques for studying photochemistry and other light-driven reactions where we can learn about the basic structure of energy levels all the way to ultra-fast dynamics of excited electrons in materials. This is here an example from my group. This is me. But energy science is not the only area where photochemistry is important. Other areas of research on light-driven chemistry in our department include, for example, photodynamic therapy for cancer treatment, photo-induced drug release, and also pigments for surface coating and self-cleaning surfaces. So speaking about surfaces are really essential for a large range of application in almost all areas of our everyday life. So several groups in the department are involved in surface science, studying, for example, how physical properties like chemical resistance or hydrophobicity of surfaces can be manipulated. So one example is this black sphere here that seems to levitate, but it's really a droplet of water that is resting on a surface that is super hydrophobic. We are studying chemical reactions at catalytic or photocatalytic surfaces. We are studying electronic properties of materials. And last but not least, we are also looking into dynamics at biological interface, like these membranes here in the top left side of the slide. So these are all very active research areas in our department. They heavily involve the spectroscopic and imaging capabilities in the department and also in facilities across campus, like the NanoFab and the Keck Center for Advanced Microscopy. And I will say a few words about these centers later on in this presentation. Now, Karl Buchs will tell us more about our research in spectroscopy and imaging and our surface analysis facility. Please, Karl.
Thanks, Lars. Next slide. So the spectroscopy and imaging group is Drew is really interesting. Well, this really spans almost all of the research areas that we've talked about before. got a good core group of people looking at using spectroscopy to understand the processes and to extract information about the chemistry in the world around us. A lot of the spectroscopy groups are also working with researchers from Winterthur Art Museum and applying this to art conservation and using the spectroscopy to directly understand and preserve our cultural heritage. Different research groups, like again, Lars Gunlock mentioned the stuff that he was doing spectroscopy. Cecil Dabowski using NMR to understand chemical reactions. Myself, Sherry Neal, Murray Johnson, and Andrew Templecoff are all doing a lot of spectroscopic research. What is interesting, next slide, or I should say exciting, if we can pop to the, is we're developing a brand new surface analysis core facility. So this is highly interdisciplinary. It revolves right now around 3 major bits of information that different faculty members have brought in, leading a major research instrumentation grants. A X-ray photoelectron spectrometer brought in largely by Joel Rosenthal and Don Watson to study surfaces. We have an AFM Raman microscope that's been around for just got a couple of years ago that I brought in through one of these grants to do state-of-the-art analysis, both in confocal microscopy, but to do tip-enhanced Raman spectroscopy to collect Raman spectra down to 10 nanometer resolution and spatial resolution. And also we got a brand new grant to bring in a time of flight secondary ion mass spectrometer, one of the few research universities in the nation to have these. And this instrument shall be coming up online the end of the summer. And we are now hiring a new facility director that will be starting in May to tie all this together. Oh, and research-wise, I should also mention we have a offer out for a new analytical/physical chemist in spectroscopy. Think we can't give too many details because she hasn't signed the offer yet, but think largely of the research that Lars is doing, but with more biochemical direction. So with that, I think I've said enough.
Thank you very much, Carl. So I will come back to our university-wide core facilities. That there are many of them, actually. I just want to mention 3 of them. I already mentioned the WM Keck Center for Advanced Microscopy and Microanalysis. And there we have multiple transmission electron microscopes, scanning electron microscopes, scanning probe microscopes, really almost everything in terms of electron imaging that you can think of. This is a facility that I'm using a lot. We have also the Advanced Materials Characterization Lab here at UD with a full array of X-ray spectroscopy, thermal and mass spectrometry, Raman spectroscopy, IR analysis. Again, basically everything that you can think of you will find there. Those centers are really on campus. You don't really have to commute to get there. They are right across the street here. We have also the Bioimaging Center at the Delaware Biotechnology Institute, which is really just a very short ride from here. And they are doing imaging, but with more of a focus on biological systems, and they can really image from the millimeter range to the nanometer scale, actually, which is pretty exciting in their lab, actually. Yeah, I should mention, so these are really all facilities that you can get trained in. So all my students basically get trained in SEM, TM. So this is really nice about these facilities. All these facilities are also directed by excellent researchers, scientists. So this is really a very great resource. In the department, back to the department, we have several departmental shops that are really essential for research, not only in repairing or fixing instrumentation, but also in building things. We have a glass blowing shop, which is not too typical for chemistry departments anymore. We have a very good electronic shop. We have a machine shop in the basement. Jody already mentioned we have 2 full-time staff for our computational IT problems. And we have a chemistry stockroom in the basement, which is also very helpful. So we have access to the more common solvents and chemicals without really having to order them. We have a library. I know nowadays this is not really too common anymore to walk into a library and actually take a real book in your hands. They do have books there. I must admit, I don't really go there very often. More important for you is that we have subscriptions to all the important journals that you will use. We have all the online database tools that you need to do your research. So you definitely have access to all literature and tools that you need for literature work. But again, I mean, if you're really into physical books, actually the library is pretty nice. I sometimes go there and just sit around and enjoy the smell of books. But I'm an old timer, so don't listen to me. Now, Jeff will introduce the CBI program for us, and I'll.
Yeah, okay, thanks, Lars. So yeah, I'll say that so UD is also home to a really prestigious NIH-funded chemistry biology interface, or CBI program. It's really very firmly embedded within the chemistry and biochemistry community in our department. And so I'm not going to go into the details of this really excellent multidisciplinary and really multi-departmental program now. But I will note that the program has had leadership that has historically come out of this department. And so this was initially led by the late Roberta Coleman, who was a biochemist in our department, and then Professor John Coe, who is a chemical biologist here, and is currently co-directed by Brian Bonson and Catherine Grimes. And so if you have detailed questions about the program or specifics about applying, which can occur actually in multiple years, either before or after you arrive at UD, I'd strongly encourage you to attend this information session here. Some of the information is at the bottom of this slide on Wednesday, March 16th. I think it's at 1 p.m. that day, but you should have received information by email, and we'll certainly send out some more reminders about this. Or you can reach out to Professor Grimes or Bonson directly, or talk to some of us about it in the biochemistry focused breakout room later today. But for now, I really just kind of wanted to focus on the fact that this is a really prestigious program from the NIH that brings a lot of additional resources to our whole department, including things like career development, mentoring, community, and is really very positive for the department as a whole. And so if you go to the next slide, this is really, I think, driven home by looking at this map. This is a recent snapshot of all the CBI programs in the country. So we have one highlighted there. And there are also CBI programs at schools like Stanford, UCSF, Harvard, Cornell has one. And I think it's very impressive to note that we were actually the first CBI program on this map. We have the longest running CBI program in the country. And I think this really speaks to the ability of our department to drive change at the national level. And I think you'll find more aspects of this in our department as you talk more to faculty and hear more about what's going on here. And I think now I'll pass it over to Don, who's going to tell us about another really fantastic NIH-funded center on campus.
Yeah, thanks, Jeff. So one of the other centers that is also funded by the NIH, we have a Center for Biomedical Research Excellence on campus that is also directed out of our department. So this is a 3-phase center grant. Each phase is about 5 years long, and we are just a little ways into the second phase. Each one of these phases provides between $7 and $12 million of funding typically for biomedical research on campus. So this has also been a huge boost to our department, helping fund things like the growth of the mass spec facility, funding many research groups, both in the department and across campus, everywhere from physical chemistry to inorganic to biochemistry and organic groups have all benefited strongly from this. So it's a real large driver in the success of the program here in the department. This is not the only center though that we have on campus. Lars, if you'll move to the next slide. There are a bunch of other multidisciplinary centers across campus. This includes things like the Delaware Biotechnology Institute, which houses a lot of resources for biology and biochemistry, including imaging, instrumentation, and other sort of high-end centers. There's a center for energy, a center for energy conversion. There's the Delaware Environmental Institute. There's two recent centers on polymer innovation. One for developing reactive materials, and another for basically figuring out how to do polymer waste upcycling. Basically, you know, the point of this slide, without going through each of these, there are a lot of interconnected, interdisciplinary centers on campus that affect most areas of research on campus, and really draw together people with like-minded interests from across campus. And that really helps bolster interdisciplinary research in the department in ways that you know, if we were an isolated silo, we wouldn't be able to participate in nearly as strongly. So I think this is really the centers in the university are really a major jewel for in the crown of the university. Lars.
Thank you, Don. So next we have Jody presenting the Allies for Culture of Inclusive Diversity.
Yeah, so in 2020, the department decided to establish a committee to ensure that we have a great climate for everybody to thrive and flourish in. This is called the Allies for a Culture of Inclusive Diversity, conveniently acronymed as the ACID Committee, which we thought would be very nice for a chemistry department. And the committee is composed of various representatives from our department, from undergrads to grad students, to postdocs, faculty, and staff. So we have representation from a little bit of everybody who participates in our community. And about once a month, we meet and discuss issues that the department might be facing, or the type of programming we might like to provide the department. We've put on seminars and workshops. We've had movie nights. We sometimes have coffee hours where we have discussions or take part in activities that help us get to know one another and communicate and explore issues of inclusion and diversity. We have a website where we provide resources for both people from underrepresented groups as well as allies for those groups. We were involved in a climate survey to assess the current status of our department as well as how to address it. We do things like send out newsletters and provide information. And importantly, we have a Community and Culture Coffee Hour that the ACID Committee is hosting tomorrow. This is in the 3:30 to 4:30 time slot. We'll have various breakout rooms for you to join to interact with current graduate students who might share similar background or interest to you, so that you can get the scoop on what it's like to be part of our department.
Thank you, Jody. So let me conclude with talking about internships and job placement for our graduate students once they have graduated. So UD is located close to many big pharmaceutical and chemical, synthetic and biotechnology companies. A couple of the names actually are down here together with national labs. And this experience provides students with the advantage to really connect and engage with these companies and national labs, and do research and internships or collaborations. And this helps students really to better understand how their skills will be used and needed in the workplace after they leave our department. So these companies also routinely visit our department and they interview and recruit our senior students as they get ready to start their independent career. So this really helps because we are actually really located close by all these companies. So student success, how do we measure student success? We really look at our students after they leave the program, how many of them are successful in their careers. And if you, this is a little bit weird here, doesn't matter. And if you just look at the numbers, oops, here, you see that, so these are the percentage of our PhD students in the chemistry program that are employed upon receiving their degrees. And you see this is for years going on almost 100%. Down here, you see the employment for 2020. So most of our students go to for-profit companies, some in government, but this is 2020. In other years, we had actually several people going to non-profit companies. Here's a list of our top employers. This includes companies and national labs again. And so with this, I want to close. I hope this shows you that it's really worth giving us good consideration. We have excellent facilities, excellent researchers, and we offer an excellent preparation and education for your career. So with this, we are open for questions. And again, you can just put them in the chat and we will read them and answer them if we can.